Good evening, everyone who join us here. Today, we will be presenting on predicting survival rates in heart failure patients using data mining techniques, a data-driven approach to clinical insights. As I assume we have already read from our slide. So this project is a collaborative effort by Hasan, Abhishek Sharma, and myself, Mubassir Sapa. Together, we have applied advanced data mining techniques to address a critical healthcare challenges. So let's dive into it, our findings and methodologies. So the primary audience for this presentation is the head of medical research institution. Our purpose is to evaluate data-driven models for heart failure prediction and analysis, providing insights that could significantly improve patients' outcome. Now we have implemented two things. Number one is classification model to predict heart failure risk using patients' data. And second one is clustering model that includes two things. Again, that is ejection fraction clustering to explore patterns in heart function. And second thing is serum creatinine clustering to investigate kidney function indicators related to heart failure. Now, the ultimate objective is to assess the potential integration of these models into clinical workflows, aiding in patients' care and decision making processes. This analysis supports evidence based strategies for personalized treatment plans. So now, what's our problem definition? So problem we address is identifying patterns in patients' data, such as serum creatinine levels and ejection fraction, to predict heart failure risk. Now, why this problem is interesting and significant? Because serum creatinine, it's a key biomarker for kidney function, which is closely linked to heart health. And second thing is ejection fraction, which is a critical measure of heart efficiency, helping identify potential failure risk. Now, early detection of heart failure risk enables timely interventions, improves patients' outcomes, and reduces healthcare costs. Through data mining, we aim to uncover these critical patterns and provide actionable insights for healthcare professionals. Now, to frame our approach, we reviewed background studies and previous work. So we did lots of things. First of all, we did research highlight a strong link between serum creatinine levels, ejection fraction, and heart failure outcomes. And additionally, we did studies which emphasizes predicting mortality risk in heart failure patients using advanced model. Now, data mining in medicine has demonstrated its utilities in its domain through two things: clustering algorithms, which help identify patient subgroups and risk patterns, and classification model, which predicts outcomes such as survival probability. Now, our approach builds upon lots of foundations, such as using k-means clustering. We group patients based on serum creatinine and ejection fraction levels, uncovering significant trends. Additionally, we also developed a classification model to predict mortality risk, distinguishing between patients who will survive and those who may not. This multifaceted approach enhanced the depth and reliability of our analysis.
So our contribution have five steps, starting with the data selection. We took the data from heart failure clinical records dataset, and dataset was already in an excellent condition, and we didn't require any major cleanups for the this dataset. And the second one is tools and libraries we used for this assignment. So the one is Scikit-learn, Pandas, NumPy, and Matplotlib. Then we do the cluster analysis. We made two models for the k-means clustering. So first one is we clustered the patients by age and serum creatinine levels, and model two is we clustered the patients by age and ejection fraction. Then we made one classification model which predict if the patient will survive or it will die. The input features were the health metrics. The last one is the evaluation and insights. So we assess the importance of the features like serum creatinine and ejection fraction in the heart failure prediction, and then we validated the model performance using the metrics such as accuracy, precision recall, and F1 score. Then moving on the crisp DM process. So we first understand the business understand we first got the business understanding. So we first made the relationship how is the features of the patients are related, like age, serum creatinine levels, ejection fraction, etc. And what is the role of predicting the heart failure risk and patient survival outcomes. The second point is the data understanding. So the dataset had already the features of age, serum creatinine levels, and ejection fraction, and the data was in the excellent condition as described before. Then we did the data preparation. We handled the missing data, and then we normalized the features for consistency in the modeling. So, as you can see, the stacked bar graph shows the count of the patients grouped by their ejection fraction values with the data divided into the survived and the deceased categories. The ejection fraction values clustered may be mainly between the 25 and 40, with fewer patients extremely low ejection fraction values. Mortality is higher in the lower ejection fraction ranges, that is 20 to 30, compared to the high ejection fraction ranges. This suggests that the reduced ejection fraction is associated with the increased risk of death. At ejection fraction greater than 40, the survival rates improved significantly, as seen by the dominance of the blue bars. So, the patients with ejection fractions around 20 to 25 have the highest counts of the deceased individuals. Moving to the next box plot. Um So this box plot compares the serum creatinine levels of the survived and the deceased groups. So survived is denoted by the green and deceased with the orange. The survivors have a lower median serum creatinine levels with values mostly clustered below 1.5 mg per dl, and the deceased patients have the higher median creatinine level with a broader distribution, as you can see, that extends well beyond the 2 mg per dl. And there are few outliers with the highest serum creatinine levels, that is more than 4 mg per dl, are evident, primarily in the deceased group, indicating possible severe kidney impairment in the cases. So next we did the modeling part. We applied the k-means clustering on the patient subgroups. So model 1 is age and serum creatinine, and the model 2 is clustered with the age and ejection fraction. And one model is on classification, and that is a predictive model for survival outcome. That is like two categorical outputs, that is survive or die. um, the next part is the evaluation, and then we analyze the clustered patterns after the model is done. We access the classification model with the accuracy and the confusion matrix. And last, the deployment. So these models can be deployed into the hospitals and the clinics. So there we can check the heart failure prediction based on the data. Yeah.
Now we'll be talking about the models that we implemented. So we implemented three models as mentioned before. The first model that I will discuss is the classification model. Basically, it's a model that predicts whether a person would die or a person would survive, given that the features, the input is some medical inputs. So we'll talk about what the input and the output will be in the upcoming slides. So what are the steps we did for the implementation is we first prepared the data. As mentioned before, the data was cleaned. We got the data from the heart failure clinical record data set, which provided us with the best clean data. So we didn't have to worry about the missing data or converting data from categoric to numeric. It was all done, and we didn't also have to worry about the outliers. Um, so after the data preparation, which was already done for us, we did shuffling. So basically, shuffle the data randomly, and then we selected the label, that is the death, whether the patient will die or not. That was our label, and the feature were all the other medical terms. And then after selecting the feature and label, we split the data into test and training. 80% of them were used for training and 20% for testing. And then we modeled the data using random forest classification, which uses decision tree in it, and we use the default parameter that is given as sklearn, which is n estimator is equal to 100. Um, I'll actually show the code of that. But before that, let me finish the slide. The accuracy was actually good. It was above 90%. And we used confusion matrix to do the evaluation and some other performance matrix such as recall and precision to visualize it. So this is the confusion matrix. As you can see that it predicted how many would survive accurately, 42, and how many would not survive, 13. So it predicted um correct mostly with 5 errors. So which is pretty good. As you can see, the accuracy rate, overall accuracy is 91%, with the precision of astonishing 0.93. The recall is a bit lower, which we could actually work on because I think it's important to have a higher recall than this. But yeah, overall, the F1 score is 0.84. So quickly going over the, my bad, it's actually here. The clustering model classification. All right, so this is our code for classification. So the first we did some imports, and then this is a helper function that actually help us make the confusion matrix. So I used the function, and the other function is just to give us the accuracy of the matrix. So this is where the function is used. Anyway, let's move on to the important stuff. First, we import the data, and then because the data was already cleaned, so we didn't have to do anything. My bad. Hold up. All right. So as you can see, data is all already clean. All of them are integers, so we didn't have to worry about them. And as you can see, there were 0 missing data. So it was everything done for us, and even the outliers were already cleared. Then I shuffle the data as mentioned. Then I get separate the features and the label, and then split the data into test and train, and then finally train the model using random forest classifier. And then this is the score, as you can see, 0.9166 as shown in the presentation, and this is the confusion matrix. Moving on. This is the clustering model. We created 2 clustering model. Again, the data preparation was the same thing. It was already done for us. For feature selection, we use age and serum creatinine. As Abhishek mentioned, that serum creatinine plays an important role. So we wanted to see how the clustering would do with age, and we actually found a good trend. Before moving on to the trend, how did we decide the clustering? How many clusters would be there? We used the elbow method. As you can see, it shows that 3 would be a good number, and for the other model, 4 was the outcome. Now, same thing for both the model. We did the same. We used the same approach, but using different features. We trained the model using k-mean clustering. We found the optimal clustering using the elbow method, and then we evaluated the clustering, the pattern, and the clustering interpretation, which I'll talk by showing you the code, or maybe this graph. So this is the clustering outcome of ejection fraction and age. Basically, ejection fraction gives us the rate at which the blood is actually pumped out per bit. So if that is low, that means you have a higher chance of heart failure, as Abhishek mentioned that in the previous graph. So we have, as you can see, we have 4 different categories, and it actually tells us that higher the age, lower is actually higher is actually ejection fraction, which is actually good. But for the other, where we compared age and serum creatinine, it's actually the opposite. Higher the age, higher is the serum creatinine, and higher the serum creatinine, the higher the probability of having heart disease. So actually, this is the trend that we found, and I'll go over the code real quick. This is the clustering thing. Again, I read the data, some imports, as you can see, and then the features, which features we're going to be using to do the clustering. So we age and ejection fraction, and this is the using the elbow method, where we find the best optimal. So in this case, the optimal seems 4, and then we use k-mean to predict, and then this is the summary. This is where we do the summary as well. As you can see that the mean age 49 has an ejection fraction of 34. As the age increases, the creatinine, I think, also sort of increases. It's kind of hard to see it here, but when you see the graph, it's a bit more easier. I've also included the description of them, which is easier for us to understand. But in conclusion, we can see that the older age group appear to have better ejection fraction, which may suggest that better heart function in this particular data set. And the same approach was taken, all elbow method, the feeding and the description, everything's there. But in this case, the conclusion we came up with is older patients tend to have higher serum creatinine levels, suggesting possible kidney dysfunction, which actually could be linked with the progression of the heart failure. So these were the two trends that we found out after the clustering, and this classification is used to basically predict whether a person will die or be alive. I think it's Mubassir's turn to take over, so I'll just move on this slide. All right, Mubassir, you go on.
Now, throughout this project, what we gain is three things: learnings, challenges, and future work. Now, what we got from learning is biomarkers like serum creatinine are critical predictors for heart failure risk, and clustering is powerful tool for segmenting patients, leading to better prediction. Now, next thing is challenges that we learned are medical data often includes variability such as missing values and outliers, which complicates analysis, and generalizing models across diverse patient profiles remain significant hurdle. Now, from future work, we aim to incorporate additional features, just further refining ejection fraction metrics to improve predictive accuracy, and furthermore, integrating clustering with other predictive models can enhance heart failure risk assessment, enabling more precise interventions. Now, as you can see, there are two links we provided. These both links shows insight into serum creatinine and its implications, and that's it. You can go through these links if you want.
All right, thank you so much, Professor.